Assalamualaikum and selamat sejahtera. In this video, I will explain how to design the capacitor of DC-DC converters. We will use these equations to determine the capacitance value of the capacitor. If you notice, the capacitor is always connected in parallel to the load. Thus, the capacitor voltage is equal to the output voltage of the converters. According to these equations, the output voltage is equal to the charge stored by the capacitor divided to the capacitance value. Eventually, the change of the output voltage is equal to the change of the charge divided to the capacitance value. In the operation of the converters, the change of the charge is equal to the area under the instantaneous capacitor current waveform. Firstly, we need to sketch the equivalent circuit of the converters when S1 turn on and turn off. As usual, I choose to design the capacitor of a buck converter. After watching this video, you can try to design the capacitor of boost and buck boost converters using the same procedures. Based on the buck converter circuit, we can draw the equivalent circuits as follows. Next, we need to apply KCL in both circuits to obtain the equation of the instantaneous capacitor current. As we can see, in both conditions, the capacitor current is equal to the instantaneous inductor current minus the output current. Once we get the equations, we need to sketch one complete cycle of the current waveforms. We will start with the inductor current waveform, followed by the output current waveform. Lastly, based on the current equation, we can sketch the capacitor current waveform. Next, we will calculate the area under the graph. According to the capacitor current waveform, the negative blue areas represent the change of charge when the capacitor is discharging, and the positive green area is referring to the change of charge when the capacitor is charging. According to the steady-state operation, the change of time of the discharging process is equal to the change of time of the charging process. Both processes take half cycle to complete. Therefore, we can label the x-axis of the current waveform like this. For the next calculation, please choose one area only, either the area during discharging process or the area during charging process. Please choose the area that you can calculate easily. For this reason, I will choose the green area. Next, based on the previous discussion, we know that the area under the graph is equal to the change of charge or delta Q. Lastly, to complete this equation, we need to find the equation of delta ILT using these following equations. You can choose either equation 1 or 2. For this procedure, I will choose equation number 2, and therefore, the equation of the capacitance value can be written as follows. Eventually, you can calculate the ripple output voltage as the fraction of the output voltage using this equation, and if this parameter is constant, therefore, the ripple output voltage percentage is indirectly proportional to the capacitance value of the capacitor. Now, let's look at this example question. We are given with these following parameter values, and we need to assume all components are ideal. Therefore, the input power of the buck converter is equal to the output power. Based on the information, we need to determine the output voltage, minimum and maximum inductor currents, and ripple output voltage of the buck converter. First, we can calculate the output voltage using this equation. It is good to memorize the output voltage equation of all DC-DC converters. Next, according to the instantaneous inductor current waveform, we can obtain these following equations to calculate the maximum and minimum amplitudes of the current waveform. Based on the equations, we need to find the value of the average inductor current. Therefore, we need to refer to the converter circuit to obtain the equation of the average current. Since IC is equal to 0, thus we can calculate the current using Ohm's law. Next, according to these equations, we need to calculate the ripple inductor current or the change of the inductor current waveform. To do so, we must refer to the equivalent circuit of the converter during S1 turn on or turn off. For this example, I choose the equivalent circuit when S1 turn on. Thus, we can have these following equations and therefore we can determine the ripple inductor current. Eventually, we can calculate the minimum and maximum amplitudes of the inductor current waveform. Lastly, we can calculate the ripple output voltage using these following equations. The next example is related to the boost converter. We are given with the resistive load, inductor value, input voltage, duty cycle and the switching frequency. And we need to determine the output voltage, output power in kilowatt, the change of the boost inductor current, delta ILT, on time and off time of the converter, and the range of the average output voltage when the duty cycle varies from 0.2 to 0.6. In total, we have 5 questions to be answered. Firstly, we can calculate the average output voltage using this equation. Based on the output voltage, we can calculate the output power and make sure you give the answer in kilowatt. Next, you can calculate the change of inductor current by referring to the equivalent circuit of the boost converter. But firstly, you need to sketch the circuit of the converter. For this example, I consider S1 closed, therefore I can have this voltage equation. And eventually I can calculate the change of inductor current or the ripple current of the boost converter. Next, based on the duty cycle, we can calculate the turn on time and the turn off time of the converter. You will calculate both parameters using the duty cycle and the switching frequency. Next, we need to determine the range of the output voltage when the duty cycle varies within this range. So from the previous calculation, we already know the output voltage of the converter when D is equal to 0.6. So when D is equal to 0.2, you need to calculate a new output voltage, and based on the answer, you can complete the range of the output voltage as follows. I will end this video with this example question. According to the statement, we need to design a buck boost converter, which means we need to determine the size of the inductor and capacitor of the converter. According to the output power, output voltage, and input voltage, we need to determine the required duty ratio. Then, we will design the inductor and capacitor based on this requirement, where the input peak-to-peak ripple current should be minimized to 10% of the average inductor current, and the output voltage ripple is not to exceed 0.5% of the output voltage. And lastly, the switching frequency of the converter is 50 kHz. First, we can calculate the duty ratio using the output voltage equation. Next, you can design the inductor value using this following solution. Eventually, we can design the capacitor of the converter as follows.